of the Quantum Flagship of the European Union, which is designed to introduce university students at a bachelor and master degree to the fascinating world of quantum science and technologies. Quantum Bits is led by 6 research centers and universities from the European Union area and from non-EU countries. This edition is hosted by the Munich Center for Quantum Science and Technology. I'm your host, Andrea Alberti. I'm senior scientist at the Max-Planck-Institute for Quantum Optics. And myself, I have several years of experience in this field of quantum simulations, and I'm now part of the Munich Quantum Valley initiative to build a quantum computer based on neutral atoms. The focus of today's event is on quantum simulations and quantum computing. We have 3 distinguished scientists from this field that will present their research activity and their point of view on future perspectives. After the 3 presentations, there will be a Q&A session where the university students and our public can ask questions to our speakers directly through the chat. The whole event is now recorded and will be made available online on the YouTube channel. Already 150 students have registered to this event, and we have received quite a few good questions already. Some of them have been already sent at the registration time. Nonetheless, I encourage everybody here in the audience to send questions in through the chat, which will then be answered later in the Q&A session. And now, before starting with our speakers, I was asked by the organizers of Quantum Bits to spend a few words to set the stage for the following presentations. So the whole field of quantum simulations and quantum computing, we can trace the origin of it back to intuition by Richard Feynman in the 1982 that realized that if we want to use classical hardware to study the dynamics and behavior of quantum systems, this is a tremendously challenging task. And the reason is that quantum systems, different than classical systems, can be at the same time in a superposition of multiple states. And the amount of resources of the memory, for example, involved to store the state of a quantum system scales exponentially with the size of the system itself, such that it becomes prohibitively hard to give a detailed descriptions of complex quantum systems. So he had this great intuition that because nature isn't classical, if you want to make a simulation of nature, you'd better make it quantum mechanical. So the idea is to use and to build quantum hardware to understand, to study the dynamics and the behavior of other quantum systems. But the whole endeavor is not simple. This is a great challenge because quantum hardware is inherently very fragile. So it simply decoheres. And in fact, this problem was well aware to physicists back then. And some believed at the time that there was no solution. There is a notable statement by Serge Haroche and Jean-Michel Armand around the mid-90s that the most ambitious task one can expect a quantum computer to perform, if nothing is done to correct for decoherence, is factorizing of a 4-bit number, which would be quite a modest achievement. However, already at that time, quantum computational scientists and quantum physicists was already working on solutions to this problem. This is Peter Shor, who came up with quantum error correction code. So this is a way to allow for correcting both type of errors, bit flips and phase flip, or any one qubit. So the idea is to take the quantum information stored in a single qubit and represent this in this type of entangled states that involve several physical qubits to represent the information of one logical qubit. And this, in principle, allows to scale up the number of qubits in the system and to correct for errors. So this opens the way, the possibility of realizing quantum algorithm for example, solving problems like factorizing numbers in an efficient way. But this didn't solve or didn't answer the conjecture of Feynman, whether we can use quantum hardware to simulate efficiently the behavior of quantum system. And the answer to this conjecture came from Seth Lloyd in the mid-90s, when he positively gave an answer to this question, and he found that quantum simulations takes an amount of time proportional to the time over which the system to be simulated evolves, which, in other words, we can do efficient, reliable quantum simulations of harder quantum systems if we build a quantum computer. And this makes the whole field very exciting and increase a lot of interest in this technology. So the reason why this technology is so exciting is there are multiple reasons. One, we just heard, there are hard problems like the one of simulating quantum systems like macromolecules that we don't know how to solve with using classical hardware. The other reason is that the Moore's law will eventually break down. We already know that transistor cost does not have every 18 months as it used to be before. And classical computers demand more and more power. So they are always more and more energy intense, the computation. And to tackle and take new challenges for these new problems, we need to find new solutions like those provided by quantum hardware. This made the interest increase in this area of science. And now there are investment in the scale already of billions of euros. And we see that countries like China and European Union are at the forefront on investment in this sector. So, and we are very happy about that. Also, the number of startups in the field has tremendously increased in recent years. So there are many companies that are spinning off from research institutes to provide solutions to practical problems in the future. And here you see a representation of a few names of companies. Some of the logos you will clearly recognize, being very notable or visible companies. Some others are smaller, agile companies that are just now being funded. And I like to mention one in particular, Planck, that is a spin-off of the Max-Planck-Institute for Quantum Optics here in Munich. And all these companies pursue different approaches to realize this quantum hardware for quantum simulation and quantum computing. So this is an overview of several technology out there. It's already slightly outdated in the numbers. Many of these numbers are already much better in these days. And one of the latest arrival in this competition, in this race, is neutral atoms that you see down here. And we have now 3 speakers that are leading figures in the field of quantum simulations and quantum computing with neutral atoms. So the idea is to take systems composed of many, in principle, from tens to thousands or even tens of thousands of atoms, and cool them down to extremely low temperatures, down to temperatures that can be in the microkelvin range, but also down to tens of nanokelvin. When the matter, these atoms behave in a very strongly interacting way. And so they experience quantum behavior, and this matter becomes very difficult to be described in terms of classical systems. And we need to really develop models to explain strongly correlated quantum mechanical system. And the great beauty of this system is that they allow to form or to study quantum models in a very controllable environment. There are still many open questions from the field of condensed matters. There are materials that we do not understand yet well, like a notable example is high TC, high temperature superconductors. And there is a belief that we can capture the essence of this material in systems like ultra-cooled atoms in optical traps. As you see here, a representation where it is possible in maybe near-term or mid-term perspective to perform quantum computing based on gate schemes, as I just spoke about it, just a while before, but now in the near term, in a different type of approach, using an analog quantum simulator approach. And I'm sure that the speaker will have much to say about that in a moment. And this is also the time when now I want to introduce the first of our speaker, with Thomas Pohl from Aarhus University. Thomas received his PhD in physics in 2005 from the Max-Planck-Institute for the physics of complex systems in Dresden, in Germany. Afterwards, he received a prestigious postdoctoral fellowship to work at the Harvard-Smithsonian Center for Astrophysics and became subsequently a Max Planck Research Group leader at the Max-Planck-Institute for the physics of complex systems in Dresden, where he also obtained his PhD before. In 2017, he joined Aarhus University in Denmark on a Niels Bohr professorship. His research interest is in quantum optical processes and collective phenomena in many body systems, such as atomic lattices, quantum gases, or semiconductors. And so with that, I'm very pleased to welcome you, Thomas. And so I'm very much looking forward to your contribution.
Okay, yeah, so thank you very much. And thanks again, Andrea. And I would also first say that this is really a fantastic initiative, and I'm really excited to give my small contribution here to this event from Aarhus University. And so this being the first talk, I kind of thought, okay, maybe I should give a brief introduction, and given the time, it will be a very brief introduction about some of the basic ideas of quantum simulations. And so you already gave a very nice introduction into some of the ideas, and of course I very much agree that you cannot start a discussion of quantum simulations without beginning with this very seminal work here by Richard Feynman. So what I just wanted to add is basically that when completing the sentence that you had just shown, so he was already, in fact, pointing out that this would be a very, very difficult task, right? So seeing that even in the early 80s, but in fact, so because it's such a challenge, I think, so this is really what makes this also such an exciting problem in physics, and he was very much pointing this out. So I think this is still a wonderful problem and a wonderful challenge to tackle for all of us, even many decades after these first ideas were put up. And so now going into like little more details, so I think one can say that there are basically two basic ideas currently to how you can perform quantum simulations. So one here on the left side is actually closer to, or much closer to how we do simulations of physical systems today with our classical computers, where you essentially encode any kind of physical system, or now quantum mechanically a state of a physical system, like shown here, this psi, into a binary language, right? So you, in our case, quantum mechanically, we would encode that into a register or a number of states represented by qubits, so zeros and ones. And as you see here already, so that's always the sort of underlying advantage of quantum mechanics, right? That if I have a given number small n of physical qubits, so this state space, so this basis set or Hilbert space that I create can be very, very large, right? So 2 to the n would be exponentially large in the number of my qubits. And then the basic idea here for this digital approach is that I always have to find a physical model, as you can see here below, and then I can now translate any kind of quantum dynamics or any kind of Hamiltonian quantum dynamics into a set of discrete operations, right? So gates, single and 2 qubit gates, and thereby I can now step by step evolve my many body quantum state, so typically a complex quantum state to any time, any degree of time. And so this can be done, and the big advantage here is that this is a very universal approach to doing quantum simulations. So in principle, if you have a complete set of gates available, you can simulate as written here in this reference down there. You can actually simulate a universe, or you have a universal quantum simulator where you can in principle simulate all sorts of Hamiltonians. But of course, this all comes with the challenge of building a working quantum computer. But right now, several of these applications have been demonstrated. So here you see an example of such a digital quantum simulation in an ion trap, using an ion trap quantum computer at the. So now I see the video is ready to start. I just don't have my mouse.
We hear you well.
Okay. So now you can see me, right? So I just gotta.
Perfect.
Okay. Yes. Yeah. So here on the right side, you actually see a simulation, right? A digital quantum simulation of a very simple molecule, H2, so the hydrogen molecule, using an ion trap quantum computer. So this really works, but of course the challenge right now is to scale this up and bring this into domain of complicated or complex chemical processes. And so what I want to focus more on here in this talk is actually the idea of an analog quantum simulation, and that is now very different from what we do with our classical computers, and perhaps more closely related to what you do with an actual experiment, right? And here the idea is sort of illustrated here with this model of the solar system is, of course, that sort of the dilemma that you might often have if you want to describe a sort of some complex processes in nature, that experimentally you might not always have access to the actual details of such a system to the degree you might have, right? So therefore, we develop models that we think describe the system, and in order to test our understanding, our theories, we have to solve these models. And quantum mechanically, solving such models is typically not possible on classical computers. And this is where this analog idea of quantum simulations comes in, going back to Feynman, that we now engineer a quantum mechanical well-controllable system, which we now have available in the experiments. You will see many or several examples of this, I'm sure, later on in the other talks. And we use that to then solve the model and then get ideas about the actual physics, or get insights into the physics of the actual system. Of course, we are not interested in solving or describing the solar system, but that could be an example that Andrea has already described. So here on the left side, a sort of complex solid state system, like, for example, understanding superconductivity. Then for that, we have to develop models. So there are Hamiltonians in that case that can describe a certain phenomenon. And then we use an analog realization. So here shown on the left, an example that, again, I'm sure you will hear about later, certainly in Immanuel's talk, actually taken from the MCQ website, where you use lattices of atoms, of cold atoms, to now emulate these kind of Hamiltonians. I give you like a few examples how this can be done later in this presentation. But let me also just point out that it is not just this direct link from a physical system to our sort of analog quantum simulators, but often you also ask this question completely out of scientific curiosity. So we also have models like gauge theories and difficult to solve models that we just want to describe and understand, and for that we can use a quantum simulator. And so one sort of big area where you or sort of a successful platform where you can realize such ideas is to use neutral atoms, and by now there are many different approaches. So you can trap like large ensembles of atoms or gases at ultra low temperatures and traps. So you create Bose-Einstein condensates, quantum degenerate gases, or bosons or condensates or fermions. And you can simulate processes in other physical systems. You can use optical lattices to trap such atoms. And again, we will hear about that. And perhaps the most recent sort of success in using neutral atoms is to use optical tweezers, so now individual traps where you can confine atoms at larger distances, and thereby, for example, use interactions between these atoms and simulate a large range of problems in quantum magnetism. And that, just in a minute, I'll say a few words about that. And then, so just to give you an example that is relevant for our research that we do in Aarhus, at Aarhus University. So you can, for example, like a very sort of elementary problem in solid state physics is if you take an electron or you study the motion of an electron in a lattice, right? And there are, of course, many processes that can go on there. But what is certainly going on is that if this electron is moving through your lattice of ions or atoms, it will interact with these atoms in the lattice and then deform such a, like these regular structures here. And while it is doing that, you can understand it by that it would create excitation. So it will create phonons in this system. And that's a very important process to understand transport properties, for example, of solid states, right? And this is can be described by a Hamiltonian that you see here. And there it just happens so that in a gas, so in a quantum gas, I can actually also realize exactly the same Hamiltonian. And the difference here is now that I can tune and control all these different parameters in my model, and I can study the physics and understand the physics. So that's an example now of using a gas as a quantum simulator. That's something we do at Aarhus University in Jan Aarts experiments. And for example, something that I cannot do, which we now succeed to do in the experiments, I can look at this in a very finely resolved, or I can look at dynamics in a very finely resolved manner. So I can, for example, watch, as sort of written here, the dynamical birth of quasi-particles, so electrons dressed by phonons directly in my quantum simulator. Then another class, and very briefly, because I think we will hear more about that later on, is now this, what I just mentioned, optical tweezer arrays of atoms. So these are like optical lattices, but at larger distances. And there people use highly excited states of atoms, so Rydberg atoms. And the idea here is that I can basically employ the atomic state, so discrete atomic levels, to realize effective spin degrees of freedom, 2 levels, 3 levels, give me higher order, higher dimensional spins. I can use laser fields to manipulate them, and I have strong interactions between these highly excited atoms to realize strong interactions between effective spins. And so as sketched here, so this is an exciting field, I think, because it really combines atomic physics and optical physics, optical science, all together also with an understanding of the underlying many-body theory, and we really have to put this together at this interface, and that's really a flourishing field at the moment, which is really taking off, and where in theory and also in the experiments. So we are really starting to be able to simulate a broad class of important physical phenomena. There's unfortunately no time to really go into any details on that and explain that, but just to take the full circle, so I think this whole challenge is still there today. So there are lots of problems that we have to solve, but it's a wonderful set of problems that we are all currently working on and solving. And many of those of these questions we are asking also at Aarhus University, so where we have recently set up a Center for Quantum Complex Systems. And there are several theory groups, several experimental groups looking into some of these ideas that I just explained. So there's a strong interest in cold Rydberg systems that we have over many years from the quantum optics side, but also trying to use those systems for quantum simulations. We look at photons, as Andrea already mentioned. There's also ideas where you can also use semiconductors to actually also do quantum simulations of quantum magnetism, for example, or other problems. We have experiments on cold atoms and cold ions, and if anyone is interested, I have no time to talk about that, of course. Go ahead, look at the website, or just contact me and ask, or if you're interested also to joining our team. We are always looking for students at the master or PhD levels. So in particular, we have very recently just set up also a master program together with university in Germany and in France, like a very new Erasmus Mundus master program on quantum technology. So if you're interested in that, again, write to me. I'm happy to give you more details on that. And I think my time is pretty much up, right? Or maybe more than that. And thank you. Yeah.
Thomas, thank you very much for this talk and this beautiful overview on the quantum simulation. So we now move to the next speaker, who is Professor Leticia Tarruell. So Leticia is a research professor at ICFO in Barcelona since 2022, so this year. There, she leads an experimental group focused on ultra-cold quantum gases, which she established in 2013. She obtained her PhD at École Normale Supérieure in Paris in 2008 and completed a postdoctoral stay at the ETH of Zurich and was for a short time CNRS researcher at the Institut d'Optique in Bordeaux, before then moving to Barcelona to start her own group. Her research focuses on quantum simulation with ultra-cooled atomic gases, particularly with bosonic mixtures and fermions in optical lattices. She has received the Young Investigator Award in Experimental Physics from the Spanish Royal Physics Society in 2015, and she has been awarded an ERC Consolidator Grant in the year 2020. So Leticia, I'm very much looking forward to your talk. So the screen is all yours. And make sure to switch on also the camera. I apologize also with the audience. Before there was some technical issue and we could not share the camera, but I think now this is solved. Leticia, we cannot hear you. If you can unmute and then switch on the camera. Perfect.
Okay, so I start again. So Andrea, thank you very much for the kind introduction. It's really nice to be here today with you and have the chance to tell you a bit about quantum simulation in general, and in particular about the type of research that we do on it in my institute at ICFO in Barcelona and in my group. So ICFO is actually not exactly in Barcelona, but in Castelldefels. This is a city in the outskirts of Barcelona. It's a bit like the Garching of Barcelona, just 20 minutes drive from Sagrada Familia. And it's actually very nice that it's only 10-minute walk from this beautiful beach and the Mediterranean Sea. So what we are interested in my group are quantum many-body systems, so systems made of many quantum particles, where the fact that we have many particles that interact with each other gives rise to new and interesting collective phenomena that do not appear at the single particle level. So basically, as Phil Anderson put it very nicely, more is different. So having more particles gives you new physics. And this can be, for example, in liquid helium, that you have superfluidity that appears. So your system moves in a frictionless way. Or in high TC superconductors, here you have superconductivity. So here the electrons pair and conduct without losses, also at relatively high temperatures that you can reach with liquid nitrogen. And then these nice high TC superconductors, they levitate in this magnetic field. And you have phenomena like superfluidity, superconductivity, also in quantum gases of bosonic or fermionic atoms. So this topic of quantum many-body systems is always mentioned along together with quantum simulation. And why is that? Because when you have many quantum particles that interact with each other strongly, then you find yourself with a system that is very hard to understand theoretically. So we are not yet really sure what's the best model to describe high TC superconductors, whether everything is contained in the toy model for that, which is the Hubbard model, of which you have here a hypothetical phase diagram, but we are also not fully sure that every phase boundary in this diagram is true. And why is that? That we don't know so well some phenomenon that was observed so long ago. It is because these systems are very hard to compute with classical machines. So if we take the best supercomputers in the world, so this is not the best supercomputer in the world, but it's the best supercomputer in Spain. It's the Mare Nostrum supercomputer that is in Barcelona. Then it would take this supercomputer much longer than the age of the universe to actually get an answer for this material. So that's why we need to follow the advice from wise people like Feynman, and then not take a classical machine to tackle this type of problem, but instead a quantum machine. And the approach that one has to follow right now, as Andrea nicely explained in his introduction, cannot be digital quantum computing, because actually it's very hard to encode the electrons of this material into qubits in an efficient way and then be able to do a simulation with enough particles. But instead, quantum simulation, analog quantum simulation, which I like to think about as a sort of quantum Lego approach. So you take another quantum system that you will use as the bricks of your Lego game, and then you will assemble with it the model that you want to solve and let your quantum particles find the solution. You will measure on them, and then you will get the answer to your problem. So in my group, we play this quantum Lego game with ultra-cold neutron atoms. Actually, today I will be talking about Bose-Einstein condensates that you see here. So you have many quantum particles that are all sharing the same quantum state. And if you configure your system right, then you can make it, for example, mimic a material like this high TC superconductor. And to do so, Immanuel will say certainly much more after me, but you take your quantum gas and then you subject it to some artificial crystal of light by making laser beams interfere. This creates what is called an optical lattice. And what is nice is that the spacing between the sites in this optical lattice, so basically the spacing between the sites in your crystal is pretty large. So if you stick a microscope objective close enough to your atoms, you can see each atom in the lattice site. So really you can get all information that you want about the behavior of this system. But actually, when I was a kid and I used to play Lego, I like making the models that were in the box that I was supposed to do. But I also had most fun just coming up with new ideas and new models, maybe not the ones that I was advised to look at. And actually, we can do the same with our quantum simulators. This type of idea has, for example, been advocated by people like Grigory Volovic using liquid helium, where he was saying, maybe not modestly, that you could basically explain the whole universe just looking at a helium droplet, at a liquid helium droplet. And in our case, we will do something like that, but not with a helium droplet, but actually with a potassium Bose-Einstein condensate. So this comes at a little bit of a price, because to make a BEC, you need to spend a couple of years in your lab to just build yourself a BEC machine, because to cool your atoms to the temperatures where the Bose-Einstein condensation transition appears, you need a lot of lasers, vacuum chambers, magnetic field coils. You need to set everything together. But once you have done that, then maybe you have the universe at your hand. So basically you have your BEC, and depending on how you set your system, you might be able to study physics like that of liquid, like water, but quantum, so more like a liquid helium, or you could be able to describe theories that are used normally, for example, to explain high energy physics or strongly correlated materials like gauge theories, or even you could simulate the expansion of particles in a curved space-times, or who knows what. I mean, really, the limit is your imagination. And actually, I will not talk today about simulating gravity with Bose-Einstein condensates, because this is something I've never done myself, but I took this picture from a paper that appeared yesterday in Nature that is really looks very interesting. I have still to read it in detail, from the group of Markus Oberthaler in Heidelberg, but I will tell you a little bit about these other two topics that we have been looking at in my lab over the last years. So one thing that we ask ourselves is whether we could study with our gaseous Bose-Einstein condensate something similar to the physics of liquids. So really to have droplets of a liquid that are self-bound and that we can study. But to do that in a system that is way more dilute and that is quantum. So if we want to do that with a Bose-Einstein condensate, of course, we need some recipe. And the recipe was given to us by Dima Petrov, a very good friend from Paris, which is to take two BECs, mix them, set the correct interactions, and just let nature do its job, and it should make a quantum liquid. And we exactly did what he said, and this was a very good recipe because it worked. So here what you see is the liquid drop made of a mixture of two Bose-Einstein condensates. And this is a very interesting liquid because it is super dilute. So it's actually 8 orders of magnitude more dilute than the air around us. But also much more interesting, it's stabilized by pure quantum effects. So the fact that this liquid exists really reveals quantum fluctuations in this system. And it's really a different type of liquid that we are that's what we are used to see. But okay, after you have done this liquid, play around a bit with it, then you want to do something else. So for example, recently we got interested in fractional quantum Hall physics. So this is the physics of quantum particles subjected to a very strong magnetic field, where one gets a very strongly correlated system that has a peculiarity, which is that when you take excitations in this system, if you take 2 of these excitations and you just exchange them, they are not behaving like fermions or like bosons, but like something in between, which is called an anion. And also this system, if you look at the edge of the system, it's pretty funny, because if you take a wave packet, like you take matter and you make it move in one direction, it will propagate without dispersion along this direction. But if it goes in the other direction, it will spread immediately. So we wonder, how do we do that with our Bose-Einstein condensate? Can we learn more about that? So there was a recipe for that. The recipe was for a gauge theory that effectively describes this edge, which said that basically we had to take the same system as before, but the two components of our Bose-Einstein condensate, we had to couple them with light, again set the correct interactions between the particles and kick them in one direction or in the other to see what happens. And then nature does its job. And this is what we saw very recently. So we have our system, a wave packet that when it moves in one direction, because we kicked it to one direction, it does not spread. Then we build a wall for it. And then when it bounces off this wall, it starts spreading. So exactly as we were expecting, and also exactly as quantum field theorists had predicted in the 90s that should happen in the model that we made, even though this model was really like a thought of theorists and had never been done in real life. Okay, so with this, I hope I have convinced you that if you have a Bose-Einstein condensate, you can actually emulate a lot of different physics and also make physical systems that only existed basically in your mind, but were not realized in nature before. And this is a quantum Lego game that, of course, I don't play alone. We play in a team. Here you see a picture of my group at ICFO. We have 3 labs, the BEC lab I was talking about today. We also have a lattice lab, and we started last month Rydberg lab. To do this work, actually, we need recipes to map all these interesting physics into our ultra-cold atom machines. And for that, we collaborate a lot with theory. So it's really very much an interplay between theorists and experimentalists discussing before we come up with the good recipes. So here in this picture is a group of Alessio Celli at the Autonomous University of Barcelona as well, with whom we collaborated very much over the last years on this gauge theories. And maybe the very last thing that I want to say, you may wonder if you go for a master thesis and then a PhD in this field, what can you do afterwards? So actually, if you see former members of our potassium lab, about 1/3 of them continued in academia, some even already getting permanent positions. Then another third continued in industry, but in quantum technologies industry. And the other third just goes to industry or consulting, really different jobs. And of course, if you're interested in this type of research, just don't hesitate to contact me. We have programs at ICFO for master thesis, for internships, of course, PhDs. So if you're interested, you can check our group website or our Twitter account and just drop me an email. So with that, thank you very much for your attention.
Leticia, thank you very much for the fantastic talk and the exciting results from your laboratories. Thank you very much. So now it's time to move to the third and last presentation before the Q&A session. This is given by Professor Immanuel Bloch. So Immanuel is Scientific Director at the Max-Planck-Institute of Quantum Optics in Garching, and is Professor for Experimental Physics at the Ludwig Maximilian University in Munich. His research focuses on quantum simulation and quantum computing based on neutral atoms in optical traps. He is one of the true pioneers in the field of quantum physics, and his work is among highly cited, for which he has been awarded several scientific prizes. The list of achievements is very long in his career, but just let me mention one in particular, which I would say initiated the whole field of quantum simulation, is the realization of a quantum phase transition from a superfluid to a Mott insulator in 2002 with his team at the Max-Planck-Institute. Immanuel, we are very much looking forward to your presentation. The screen is all yours.
All right, thanks a lot, Andrea. I hope you can hear me. Do you hear me? Okay, very good. Excellent. So yeah, it's a real pleasure to be with you today and give you a little bit of overview of what we're doing in Garching here at MPQ and LMU, and discuss with you in the discussion section later on. Thomas and Leticia have already given a great introduction and explaining their research. So some things probably will be doubled a little bit, but I don't think it matters so much if you hear some things again in a different language. So, you know, when I started entering this field, what really motivated me was that I saw that really we have a chance to have new tools to understand quantum any-body systems at a really profound level, to realize new kind of materials that actually we don't have in nature even. And so this was really, you know, the starting point for my own career in this field. But now, of course, this has become a whole if you look now at the whole field of quantum science and technology, it's a booming research field ranging over quantum simulation, computing to communication, sensors, materials, and it's really become a huge and exciting field. Of course, when you have new technology fields, there's always this tension between hope and hype that you have there. And of course, there are a lot of expectations what these new machines will be able to do. And I, have a lot of hopes also. I try to stay away from the hype field, but typically there's this intersection of reality where hope meets hype, and which we scientists try to stay. So you've already heard from Leticia and Thomas the two different paradigms for quantum computing, either the analog one, which we now call quantum simulation, where you basically try to directly implement the rule set of a certain Hamiltonian, for example, the Fermi-Hubbard model or something more exotic, and you let that run, and you get, for example, the time evolution of the system, or you find the ground state of the system. The nice thing is, if you can do this directly in your system, it's actually very resourceful. It uses the quantum resources extremely efficiently. But of course, the downside is you can only simulate what you can really map to your artificial quantum system. So you're typically not universal. So you can't simulate everything that somebody would give to you. On the other hand, you have this digital approach where you break down the time evolution, for example, in this trotterized description into discrete gate sets. And you have the discrete time steps at which you involve the system. And this is actually very powerful because based on these single and 2-qubit operations, you can basically realize an arbitrary rule set. You can become universal. But of course, there's a very big price to pay for that. And maybe we can discuss, how big this price is to make a meaningful, digital quantum computation. For example, in quantum chemistry, you have a huge resource overhead, of course, here that you have to realize. So two approaches are followed in many systems. Sometimes people ask me, well, analog, haven't we moved today from analog to digital in electronics? And that's, of course, true if you think of the first computers that were built. But actually, there's a huge revival now in electronics to use analog electronics also for classical electronic systems. So because for certain type of applications, specifically apparently in the context of artificial intelligence and machine learning, there's huge advantages of doing calculations in an analog way and not in a digital way. So just want to show you that, sometimes pursuing this analog way for specific applications can have distinct advantages. So as Thomas and Leticia were already saying, we're working a lot also in these optical lattices. So you see a beautiful picture of such an optical lattice here to the right. It's an interference pattern of these laser beams. We can trap atoms there. We can realize different spin states, for example, via microwave transitions or optical clock transitions, which realize qubits in our systems. And we can typically do this with a few hundreds to a few thousands of particles. And actually, what's the biggest difference, I think, to any other quantum computing platforms is we can let the particles move around in this lattice. And therefore, it doesn't matter whether you have fermions or bosons. And particularly if you use fermionic particles, isotopes of neutral atoms, you can directly simulate the behavior of electrons, for example, in a real material. And you can observe these systems with microscopes. You see here a very nice picture of a former postdoc of mine, Ji-Yeon Choi, in Korea, who took this image through a quantum gas microscope, where you see, thousands of atoms imaged. You can see each individual particle lighting up. You can engineer potentials. You can address the particles in these lattices. So it really gives you a lot of flexibility. The other approach was these tweezers that also came up. I show here a picture from Antoine Rouet's group in Paris, where you basically trap the atoms in the foci of laser beams. So they're like optical lattices, but with a little bit more flexibility, that you can move the tweezers around to arbitrary positions and thereby position the atoms at arbitrary positions. The downside is that you can only do this at larger distances, order of magnitude, typically larger distances, and you can't bring the atoms so close together, so tightly confining as you typically have them in the optical lattices. But this is a very nice geometry, and by using, for example, these Rydberg interactions, you can realize quantum gates between individual atoms, and you could reconfigure the array, introduce new kind of interactions in the system, and basically change the topology of your quantum computation on the fly. This is subsumized here in this picture that you also saw from Thomas in this nice review from Shannon Whitlock's group, where you basically can think of now the architecture for a quantum computer or quantum simulator based on these atoms, would be these neutral atoms stored either in optical lattices or tweezers. We can address them, we can coherently manipulate their spin state, we can do single qubit operations by sending light pulses onto the atoms. We can also realize 2-qubit gate operations by having Rydberg interactions, for example, between two of those atoms, which realize very strong and effective fast quantum gate operations. You see, a lot is needed to realize this. You have classical control hardware, you have the whole addressing schemes, you have the whole readout schemes through CCD cameras. So all of this has to come together, and it really is a marvel of photonics engineering to bring this together to make this a really working and powerful system. So just to give you an idea, one problem one has to solve is how to send these laser pulses, this many laser pulses, thousands of these laser pulses in a very precise way onto the atoms to realize these quantum gates. And one way how to do that is, of course, you need an integrated approach for that. And one way we're pursuing, for example, is also to build these integrated photonic circuits with modulators where you can basically turn on and off very quickly a vast array of laser pulses onto the atom to realize the quantum gates between them. And then, of course, you want to go from a lab like this. This is one of our labs in Garching, this complex setup that you can see here that's really quite overwhelming, to something that's more integrated, more stable. So, we also have to work a lot together with laser companies, and we're doing that with Mendel Systems and Toptica Photonics, for example, to provide us with this next generation of completely integrated rack-based laser system, where hopefully, for us, the operation will be as simple as turning on your, microwave synthesizer and getting the desired laser pulses with phase and amplitude control, as you do, for example, from a Rode and Schwarz microwave generator. So this is where the future is going, and we'll of course have to see how good these systems are, but it will be definitely a big step forward in the reliability and the powerfulness of this approach in getting things going. So finally, maybe where do we stand? I told you about this analog model, quantum simulation. Also, Leticia and Thomas talked a lot about this. And we have the digital circuit model, which is kind of the favorite model in quantum computing. Actually, maybe the best part of everything lies somewhere in between. Is often that you combine hybrid analog digital operations to have the most powerful, the benefits of both worlds, of having the powerfulness of the analog simulation together with the versatility, with the more universal operations that you can realize in this digital world. So I think this is probably for the next many years to come, this will be maybe the most exciting field where you can work, and you can read a little bit about these ideas in a recent review we wrote together with Peter Zoller, Matthias Treuer, and Andrew Daly. Yeah, finally, let me just finish off and just thanking MCQST also for hosting our event today, and Andrea being our moderator will guide us later through your questions. And as the other said, let me just highlight a little bit opportunities in Munich. So if you want to find out what's going on in Munich in quantum, the best place to start looking is this our Cluster of Excellence website, the Munich Center of Quantum Science and Technology, MCQST. You'll find a lot of information about how to apply as a student, what kind of talks and events are going on in the system, about our new master program, which right now we have about 80 students every year that are joining in Munich in this master program, and we have graduate courses. So everything as a first starting point, you can just go to that website, have a look, and see if Munich is also a place for you where we'd like to work. And with that, yeah, I thanks for your attention, and I'm looking forward to the questions in our discussion.
Immanuel, thank you very much for the great talk and for sharing with us all these beautiful perspectives for the future of digital, analog, and now hybrid quantum computing and simulations. So at this point, we can move to the Q&A session. So I would like to ask all the speakers to switch on the camera. And in fact, so we received already quite a few questions from the participants, but I would like to start from one question that you, Immanuel, inspired me. So you said you gave some hint about the motivation that drove you to enter this field. So I would like to ask all the three speakers to shortly give a comment about what was your motivation when you were a student, maybe at the time of bachelor or master, to join this exciting field of quantum optics and quantum technologies. And also, perhaps if you can comment whether it was an easy decision to choose for theory or an experiment in your case. So maybe we start, I suggest we start with Leticia and then Thomas, and then we close with Immanuel if you want to add any remark on top of what you just said.
Okay, so I can explain how I came to experimental quantum simulation with cold atoms. Actually, I was not supposed to do that. As a student, I moved for an exchange semester in Paris with an Erasmus scholarship. And then when you're an Erasmus student, you can do a bit whatever you want. So I thought I should try many different things to see what I liked. And at the time, I was very convinced I would be a theorist. But among the different things that I tried, there was a bit of a bibliographic project in a high energy physics institute. There was also a very interesting course on atomic and molecular physics. So I ended up in a cold atom group. And after 1 week there in the group of Jean Dalibard at INS in Paris, I realized I will be an experimentalist because just seeing things in the lab, I liked it so much more than just seeing it in an equation. So I think this is to say that maybe people should really try out things before thinking that what the a priori that they had of what they should do is the right thing. Huh?
Great answer. Thomas.
Yes, so I actually did not start my career, so to say, in quantum physics at all. So when I, like my PhD, that was in Dresden, as you mentioned, right, at the Max-Planck-Institute, was actually on plasma physics. So that's how I started, and then at ultra-cold plasmas. And then we actually saw that in these plasmas, you had Rydberg atoms forming, and then my interest changed to Rydberg atoms. And then really as this field evolved itself, sort of my interest and the activities evolved, right? And at the time, like this started, like the work, like 15 years ago, let's say, like this work on cold Rydberg atoms was a very tiny community, actually, like a very small field, like a nice community and exciting work, but was actually small scale. And now you look at it, it's a very sort of successful technology for quantum optics, but also these simulations. So it's just, I think, also an example how sort of how quickly this field is evolving, right? And then your activities are evolving. So now we do many body physics as well. And I think that's what makes it exciting, that you are not, you know, sort of confined to one direction, and you can change your or evolve and broaden your activities. And this will keep going, I think. So the change is actually going. Immanuel like talked about the other ideas. Is also connecting to computer science now, right? Like a lot of work on that. Yes.
Thank you, Thomas. Thank you. And Immanuel, if you said it was about tools, but do you want to add anything more?
Right, just quickly, maybe I think, you know, definitely I enjoyed theory in the beginning, but I also noticed I'm too much a fan of being in the lab and tweaking things and technological things and working on, you know, experimenting. So, and actually I wasn't really good enough for theory either. Also, that also helped in the decision, you know, what to do. And I think quantum, you know, was really, quantum mechanics for me was the most exciting lecture I had in my physics study. And that really, because it was so different than anything else we had been working on, and the concepts of quantum mechanics, that really fascinated me, and I wanted to work in that. And then I saw this, you know, this Bose-Einstein condensates coming up, and I really felt, you know, that I want to do that. Even though people told me, you know, I will not quote them now, good colleagues that really have a high opinion of told me, you know, don't do BC, everything has been done, you know, and it was, you know, 3 years after BC, don't do BC, everything has been done already in cold atoms that you could do. So I think this just shows how older colleagues, or, you know, if you know, you can get things quite wrong if you want to make predictions where things go. And I'm very happy to have chosen the field.
Great, it was beautiful. Yeah, please, Thomas.
I can add something, like just when you like said this last remark. So that's pretty much in line with advices that I actually got. So when I decided, you know, to go into this quantum from this more classical Rydberg physics, so the established people actually told me as a PhD student or at the end of my PhD, so this is never going to work. Like, you know, like don't spend your time on that. And perhaps that's a repeating pattern, right? So maybe that's also the most exciting directions where you don't foresee sort of implications this might have for everyone.
So it was great to hear from you, your answers. So here's the next question. Maybe I would address it to Thomas, since the ball is in your field. So you were just now on the microphone. So this comes from Rasmubramanya Raja. And the question is, where do you see the field of quantum simulation in the next decade? What do you think will be the next major breakthrough? It's a challenging question to read into the future, but it would be great if you share with us some of your thoughts.
It's definitely difficult, and I think like all three of us can sort of answer that equally well or give different perspectives. So I think it's also Immanuel mentioned that, right? So like you have these two directions, digital and analog, and they both have their problems, right? So I think with the analog simulations, like a lot of progress has been made. So there are lots of technical challenges for like lowering temperatures, for example, so to really keep up the promises on the experimental side. So what we find interesting now is also like there has been lots of work on looking at closed systems. So I mean, it has been the advantages of cold atoms and BECs to have cold systems, but I think ideas are also moving into studying open systems, so understanding how measurements on many body systems work, right? Or also maybe in these Rydberg simulators, how we can simulate temperature. But to really make a big step, and Immanuel mentioned that, is to combine these ideas, right? And have hybrid approaches, like combining classical and quantum. That's already happening. So there are many directions, and like predicting the big breakthrough, I would not want to do that, because the big breakthroughs are always the things that we don't expect to happen actually.
So. Of course. So we have many questions. So if any of the other speakers want to add something, please feel free to do so. Otherwise, I can just throw some other question out there. So one question that is, I think, quite relevant now for the young students is, what is your advice that you would give to students to get into this field? Or what about if some student comes from informatics and engineering studies? So is there any type of research career for them in the quantum field? So maybe I ask Immanuel to take this question.
Sure. I mean, I think, first of all, I think you have to choose something you're really fascinated by. I mean, as a student, the biggest advice I always give to them, because you can only be successful in something you really enjoy doing. And if you don't enjoy, if you consider it as a work, where you feel, okay, this is my 9-to-5 job, don't do it, do something else. And you really be fascinated what you're doing. That's number one, most important advice I always give to students. Then, of course, try to take internships in groups, try to see, do I like working in this field? Do I work in these groups? And try out a few different things. Try out a few different internships with different groups, maybe in the place where you are, or go abroad or to a different country for a semester or so to try out and see the first phase, where you're trying to find out what to do next. And you can always still switch. There's never a point where you can't switch. So I think, but that would be my biggest advice. Maybe if you start as a young student in the field, trying to start somewhere, try out a few different things and see what you get most excited about.
Okay, great. And actually, there is a very related question that at this point I would address to Leticia. So this is about, so I read the question. I was told that it is mainly men who are active in the field. What advice can you give to young women to get involved and pursue a career in quantum science technology?
Okay, so when I started my PhD, I was the only girl in the team. And then it's true that in general, I mean, also when I moved for a postdoc, we were 2 in the whole group and so on. But I think things are changing. There are more and more women joining. And I think you should not be shy. I mean, you should just reach out. And and go and do internships and so on, I always find in my group that I have a huge advantage, that there will always be a woman because I'm there. But I also see that things are changing. Initially, when I started the group, I did not have any women applying, and now I have more and more, and we are almost 50-50. So I just think that there is not a gender reason why men should do that or women should do that. You should just be brave and apply. I find men are, more easily reaching out to me than women. I don't know why. So just don't be scared of that and go on.
Great answer. So we are still receiving many questions, and more are coming. So I just read maybe one or another question before we wrap up, since time is slowly running over. So this question is about where do you see the most promising perspectives for quantum advantage in the different quantum platforms for the future years? I guess in the near midterm. And perhaps if I can add to this question, perhaps you can highlight what you think is the advantage of neutral atoms, as you all are leading figures in this field. So I would ask then Immanuel to comment on this question.
Sure. I mean, okay, there's this famous quote, you know, predictions from Mark Twain, predictions are very difficult, especially when they concern the future, but let me try. You know, I think definitely, I mean, I'm very sure scientific applications is where we're going to see the quantum advantages, probably not so much in industrial applications like optimization questions. I'm a bit more pessimistic on those questions, that they can be better done on a than on a classical computer, because there's just extremely powerful heuristics also. But you know, intrinsically, quantum problems where the quantumness is hard for classical systems are exactly systems where I think we're going to see more and more quantum advantage issues, and we're already seeing that. Keep in mind that quantum advantage is a little bit ill-defined because it's a moving target. It's not a point we reach and we can claim we have now reached a point where quantum machines are better than classical machines. It's always going to be basically a competition between the two, and showing you can do something on a quantum machine you can't do on a classical machine. Then somebody comes with a great classical algorithm and improves that. But I mean, that's progress works, and that's also how these systems can be very useful, I think, in advancing, you know, also our knowledge of how to simulate quantum mechanics with classical computers. So this interplay theory experiment is extremely important, and that's where I see the biggest chances.
Okay, great. So we have still a couple of questions. Maybe I ask to give an answer to Thomas and then Leticia, starting with Thomas. So the question is, if I want to learn about simulating quantum system, where and how should I start? How much should I need to understand the hardware details? So I presume this question comes from someone that has more like informatics background.
Yes, so I think, I mean, that's kind of what I try to sort of describe in the presentation, right? So the basic ideas are actually quite similar, right, for all of these platforms. So we mostly talked about cold atoms here, right? But they're like very same ideas are used for using photons even, right? Where you can generate interactions now completely differently, so measurement processes. So we use solid state systems to do quantum simulations, and from the theory side, and we work on all of these problems basically. That's the beauty about quantum mechanics, that it's actually that the theory is it's in principle quite simple, right? It's very difficult to solve them. That's why we need quantum simulators, but the concepts are very universal, right? And you said it, like computational science is actually feeding into that. There are lots of, or there's growing overlap with that. Right? So I think, so the hardware, and I don't want to offend the experimental colleagues, but for the concepts, the hardware is actually not that important, right? But on the other hand, you also work on the theory side to exploit like a certain hardware, right? Like to find designed approaches that are particularly good for atoms or particularly good for using ions and so on. So I think it's an interplay of both, right? Like general concepts and also doing hands-on atomic physics and optical science and so on.
Great, Thomas, thank you. So now the last question. There are really many good questions, and I'm sorry that we can't cover all of them. So the last question is about industrial perspective after, let's say, studies in quantum, in this quantum field, or a PhD in the quantum field. Here, someone is interested to know about industrial opportunities in quantum computing and how to prepare ourselves for it. I would ask Leticia, that already mentioned some of your members or former members in your group that moved to industry. Maybe you can elaborate or expand a little bit more on that.
Okay, sure. So I have a young group, so I don't have so many former group members, but what I can say is after a PhD or a postdoc in ultra-cold atoms, you know many experimental techniques, laser physics, electronics, computer control, that are very useful in many different industries. So 1/3 of the people actually got very nice offers in quantum technologies companies. So in projects making inertial sensors with cold atoms. So we had a postdoc moving to that. So he kept doing cold atoms, but now in a more applied setting. And another PhD student, well, we have a quantum technology startup at ICFO, QSide, that makes quantum random number generators. So he just moved across the street and is having a lot of fun on that. I mean, we see him very regularly because we are so close. And I mean, these are jobs that are industry, but stay pretty close to what they were doing in our labs. Then there are also people that take different opportunities in industry. I mean, you know a lot about lasers. So now I have a former postdoc that is developing lasers for checking your eye for ophthalmology, and they need fast lasers that they can scan well, that are actually not so far from the lasers we were building in the lab. So you really have different possibilities. I see that more and more people take also industrial careers because there are things that are super interesting there. So I think it's a very nice opportunity too.
Yes, this is great, and a great point now to come to a close for this event. I would like to thank very much again all these three speakers for the fantastic talks and the perspective and thoughts that they could share with us. Also, I would like to thank the host and organizer of this event, that this time at the Munich Center for Quantum Science and Technology, the MQST, and also the people behind it. These are Anka Ionescu, Tatiana Wilk, and Claudia Leonard. Thank you very much, and thank our audience and students for following us.